air is removed from it. The bowl is open to atmosphere and contains mercury. With no air in the tube, there is nothing to stop the pressure of the atmosphere pushing up the tube, and the mercury has risen to a height such that the pressure it produces at point X is equal to the atmospheric pressure. The vertical distance from the surface of the mercury in the dish to the top of the mercury meniscus in the tube is the measure of the atmospheric pressure. The higher the column, greater the atmospheric pressure. The space above the mercury contains no air, although it does contain mercury vapor. Here, there is another barometer. We are marking some points A, B, C, like D, E, F, like that. We should know what is the pressure at each and every point. As I already told you, at the top it's vacuum. So what is the pressure at this point, PA? PA is equal to, here, PA is 0 centimeter of mercury. If you check the point PB, the second point PB, PB is 26 centimeter of mercury, because this height is, from this point to this height is 26 centimeter, it's mercury, so 26 centimeter of mercury. And then PE, here, I told this is the balancing point. This height is how much? 26 plus 50 is 76. So at the pressure here is 76 centimeter of mercury. So remember, at pressure at A is 0 centimeter mercury, B 26 centimeter of mercury, and also at E 76. If I take another point F here, pressure at F is, this is 76 plus this 8. 76 plus 8, 84 centimeter of mercury. Now, for a given liquid, the pressure will be same at the same level. Therefore, pressure at D and E are equal. So this D and C, these two are equal. Why? Because this height is not much difference, only 50 centimeter difference. In that 50 centimeter difference, the pressure won't vary. So these 2 points have the same pressure. The difference of the gas pressure at different level can be ignored if the distance of the height is not too large. Therefore, pressure at E and D is 76. And one more thing, the pressure at E and pressure at D are equal in this situation, because both are atmospheric pressure. The next one, how will you convert the millimeter of mercury? That is, the normal atmospheric pressure is 760 millimeter of mercury is the standard atmospheric pressure, that is 1 atm. Its value in Pascal can be found by using the formula shown here. So we need to convert millimeter of mercury to Pascal. How will you convert? First of all, we need to use the formula pressure equal to rho GH, whereas rho is the density, here the density of mercury, and G is gravitational field strength, and H is height. The height is given in millimeter. First of all, we need to convert the millimeter to meter. So what we need to do, we need to divide this 760 millimeter to meter by dividing it by 1000. So you will be getting 0.76 is the height, and 13,600 is the density of mercury, and 10 is the acceleration due to gravity. So the final answer is 1.3360 Pascal. So that is the total atmospheric pressure. So this is equal to 760 millimeter of mercury. So 760 millimeter of mercury is equal to 103,360 Pascal. The value of standard atmospheric pressure is roughly approximately equal to 100,000 Pascal. So this is the way to convert millimeter of mercury to centimeter of mercury. Here you need to remember the SI unit. So the millimeter you need to convert to meter, and then the density is already, if it is given in kilogram per meter cube, no need of changing. The next one, the atmospheric pressure, the difference in height, this height from the surface to the top does not depend upon the width of the tube. Whether if you use a wide tube or a narrow tube, it won't change. The height of the mercury remains same even though the diameter of the glass tube is different. Second one, the height of the mercury remains the same even though the glass tube is lifted up or lowered down. Here you are lifting up, this is lowered down. In both cases, the vertical height will be same. Normal atmosphere means it is 760 millimeter of mercury. And the third one here, the vertical height remains the same even though the glass tube is slanted or tilted. This will be again 76 centimeter of mercury. 76 centimeter, so the atmospheric pressure is 76 centimeter of mercury. So it is a constant value. Then what are the advantages of using mercury as a barometric liquid? What are the advantages? The density of mercury is 13,600 kilogram per meter cube, is greater than of all other liquids. So only 0.76 meter height of the mercury column is needed to balance the normal atmospheric pressure. So if you use mercury, we can use a tube of length only 1 meter is enough. That is, it will rise only 76 centimeter. The vapor pressure of mercury is negligible, so it does not affect the barometric height. Mercury neither wets nor does it stick to the glass tube, so it will not stick to the glass tube mercury. The surface of mercury is shining and opaque, therefore it is easily seen while taking observation. So these are the advantages of using mercury barometer. Then if you use, what are the disadvantages of using water as a barometric liquid? We can use water, but if you use water, water is low density. Its density is 1000 kilogram per meter. So if you use water as a barometric liquid, the problem is the water level rises to nearly 10.4 meter. So we have to use a long tube, which is very difficult to carry from one place to another. The vapor pressure of water is high, so the vapor which may produce in the vacuum space makes the reading inaccurate. The water vapor will exert a force on the water surface, so the level decreases and we will not get the correct answer. Water wets or it sticks to the glass tube, therefore makes the reading inaccurate. Water being transparent is not clearly seen while taking the observation. I have taken some past paper questions from the past paper book. I am going to discuss some questions here. First question, the diagram shows a simple mercury barometer. You know what is the use of a barometer? It is used to measure atmospheric pressure. Well, which height is the measure of atmospheric pressure? Height, that height C. Say, look at this one, from the surface to the top upper meniscus. So this is the answer. All others are not correct. A barometer is carried from the first floor to the 20th floor of the building. Why does the reading on the barometer falls? Why the reading on the barometer falls? So reading falls because of low pressure. So go through the readings. First one, air pressure has increased, wrong. Gravity has decreased, that also wrong, because gravity will not change within this 20th floor. Temperature has increased, no. There is less air above the barometer, so less air, so the atmospheric pressure decreases. There is another third question. Figure 3.1 shows a glass tube dipped into mercury. The vacuum pump is connected to the top of the tube and switched on. The mercury rises up the tube and stops. Mercury rises and stops up to 0.76 meter height. Question A. 3 points on figure 3.1 are labeled P, Q and R. P, Q and R. State which 2 points are in the atmospheric pressure. State which 2 points are in the atmospheric pressure. You should know that here this is atmospheric pressure and this also atmospheric pressure. One question is done. Then second one, the density of mercury is 13,600 kilogram per meter cube and the gravitational field strength G is 10 Newton per kilogram. Calculate the pressure due to the column of mercury. So how will you find this one? Pressure equal to rho G H. You need to use rho 13,600 multiplied by 10 and height is 0.76. So you will get the answer which is in Pascal. Now the last question, state and explain what happens if the mercury in the apparatus shown in figure 3.1 is replaced with water. If you change the mercury into water, what will happen? You know water is less dense than mercury. The density of water is very low. Its density is 1000 kilogram per meter cube. So if you use water as a barometric liquid, the height rises to nearly 10 meter. So it will rise and goes into the vacuum pump even. That's all about this topic, that is barometer.